last class we have seen the use of semaphore variables, and we have defined a semaphore variable S, which can be only initialized, and two operations can be performed on the semaphore variables other than initialization. One is PS operation, which is defined like this: while S is less than or equal to 0, do skip, then decrement S by 1, and the VS operation, where S is incremented by 1, and we have also said that both these PS and VS operations, they are atomic in nature. And we have seen the use of semaphore variables to solve the mutual exclusion problems, where we have taken one semaphore variable, say mutex, which is initialized to a value 1. Then for the critical section problem or mutual exclusion problem, before entering the critical section, in the entry section you perform P mutex operation, and in the exit section you perform V mutex operation. So this will give the mutual exclusion property. We have also seen the use of semaphore variables for process synchronization. So whenever we have a statement, say Sj, which is to be executed only after Si, you use a semaphore variable, say sync, which is initialized to a value 0. Before execution of Sj, you perform P sync operation, and after execution of Si, you perform V sync operation. So this ensures that Sj can be executed only after Si. So even if Si and Sj, they are the statements being executed by two independent processes, but because of this P sync and V sync operations, these two processes will be synchronized at this point. Then we have redefined the operations P and V on the semaphore variables to avoid the busy waiting problem, where instead of having a semaphore to assume only the integer values, we have defined semaphore as a structure having an integer value as well as a list associated with it. So whenever a process tries to perform P operation, if it finds that the semaphore is not free, that is the value of semaphore is not greater than 0, then the process will be added to the list for that particular semaphore variable, and the process will be blocked, or the process will go to sleep mode, so that it does not consume any CPU time. The process will be waken up only when some other process performs a V operation on the same semaphore, removes a process from the list, and puts that process in the ready list. Okay, so that is how we can avoid busy waiting of the processes, in the sense that the process does not consume CPU time unnecessarily. So let us see how these semaphore variables can be used for different problems with the help of some classical problems. One of them, of course, we have seen earlier, that is a producer-consumer problem. We have seen two different solutions of this producer-consumer problem earlier. Now let us see whether we can solve this producer-consumer problem using the semaphore variables as well. So to solve this producer-consumer problem, we assume that there are three semaphore variables. One of the semaphore variables is full, other semaphore variables is empty, and the other one is, say, mutex. All these are semaphore variables. And as before, we have two other variables. One is next P, other one is next C, and they are of type item. Okay. Then we assume that the semaphore variable full is initialized to value 0, empty is initialized to n, and mutex is initialized to value 1. So, this is the initialization of all these semaphore variables. Then the producer problem can be written like this. I put it under repeat until false. Okay. So, you can write the producer and consumer processes like this. So, whenever a producer process produces an item and wants to put that item into the buffer, firstly the producer process will perform a p-empty operation. Okay. And you find that empty is initially n, that means initially all the locations in the buffer are empty, there is no item in the buffer. Because of this p-empty operation, whenever this p-empty operation is successful, every time the value of the semaphore variable will empty will be decremented by 1. So, you find that in case of a semaphore variable, every p operation on the semaphore variable decrements the value of the semaphore variable by 1. Okay. And after decrementation, if it finds that the value is less than 0, in that case the process will be blocked. So, here also first the producer process performs this p-empty operation, and because of this it is quite obvious that the value of this semaphore variable empty indicates how many locations in the buffer are free. Okay. So, whenever value of empty will come down to 0, that means the buffer is full. Okay. So if this PMT operation is not successful, in that case we know that the buffer is full, so the producer process cannot put this item into the buffer. So the producer process will be blocked. In case any location in the buffer is free, in that case PMT operation will be successful and the producer process will not be blocked. So it can put this item which has been produced in next P into the buffer. Okay. So before putting this item into the buffer, it performs P mutex operation, and this mutex semaphore variable allows only either the producer process or the consumer process to access the buffer at a time. Okay. So it maintains the mutual exclusion of the buffer. Both producer process and consumer process cannot access the buffer at the same instant of time. So that is ensured by this mutex semaphore variable, right? So after that, if P mutex is also successful, this next P, the item will be added into the buffer. After that, the buffer will be freed by performing V mutex operation, and then by performing V full operation, it will indicate that one more element, one more item has been added to the buffer, because V full operation will increment the value of the semaphore variable full by 1. Okay. Similarly, for this consumer process, it has to perform P full operation, because if the value of this variable full, integer value of this variable full is less than 0, that indicates that there is no element in the buffer to be consumed. So the consumer process has to be blocked. So it performs the P full operation. After that, again P mutex and V mutex, this pair of operations ensures that access of the buffer is mutually exclusive. If both of them are successful, both P full and P mutex operations, then only the consumer process will consume an item from the buffer, and after that, by performing V mutex operation, the buffer will be full, buffer will be freed, and finally, by executing this V empty operation, because the consumer process has consumed one item, so one more location in the buffer has been made free. Okay. So the value of the semaphore variable empty will be incremented by 1 by this V empty operation. Okay. So you find that in addition to the other two solutions that we have discussed earlier, this producer consumer problem can also be solved by using the semaphore variables. Okay. Now let us take another classical problem. I am discussing all these classical problems because they are common problems in operating system. Okay. So the next problem that we will discuss is called a reader-writer problem. Now, what is this reader-writer problem? Here we assume that suppose we have a shared file. Okay. The file can be accessed by a number of reader processes. It can also be accessed by a number of writer processes. Okay. Now, it is quite obvious that we can allow more than one reader process to access the file simultaneously, because none of the reader processes are going to modify the content of the file. But if it is a writer process, then the writer process will obviously change the content of the file. So if there is any writer process accessing the file, no other process, whether it is a reader process or writer process, should be allowed to access the file. Okay. So only one writer process should be allowed to access the file at a time, whereas more than one reader process can be allowed to access the file simultaneously. But whenever there is a writer process which is modifying the content of the file, no other reader process or writer process should be allowed to access the file. Okay. Similarly, if there is at least one reader process accessing the file, no writer process should be allowed to access the file. Okay. And this is a common problem, and this conclusion will also come from the read set and write set that we have already discussed. Okay. So given this kind of problem, how this problem can be solved by using the semaphore variables. Okay. So let us try to write the solution. We'll assume that we have two semaphore variables. One is the mutex and other one is the write. They are of type semaphore. And we assume that both these semaphore variables, mutex and write, they are initialized to a value 1. So this is the initial value of mutex and write. We use one more integer variable, say read count. So this read count is an integer variable, and we assume that initially the value of this read count is equal to 0. Okay. So after this, we can write the codes for the reader process and the writer process like this. For the reader process, first we perform p mutex operation. After that, you increment the read count by 1. Then if read count is equal to 1, then p write. Okay, then you perform v mutex. Then the reader process goes on reading the file. Then at the end, it will again perform p mutex operation, decrement the read count, okay. So this will be the structure of a reader process. Similarly, for a writer process, the structure is much simpler. First, it has to perform a p write operation. After p write is successful, it modifies the file, that is writes into the file, and finally it performs a v write operation. Now let us see how this thing works. You find that we have used two semaphore variables, one is mutex and one is write, and there is one integer variable which is read count. Read count is initialized to 0, and both the semaphore variables, mutex and write, they are initialized to value 1. Okay. What does the reader process do? Every reader process will have similar code. Similarly, every writer process will have similar code. Okay. So reader process first performs p mutex operation. Then within this p mutex v mutex pair, a reader process modifies or increments the value of read count. Then if read count equal to 1, then the reader process will perform p write operation. If the read count is not 1, then this p write operation will not be performed. Now, what is the significance of this? I have a number of reader processes. every reader process, whenever it wants to read contents of the file, it has to perform these statements, execute these statements first. Okay. Now, whenever one reader process performs this pmutex operation, until and unless it performs the corresponding vmutex operation, no other reader process can enter this part. Okay. So, the first reader process, after performing pmutex operation, it will try to modify this read count and will try to perform this if statement. Okay. So, before it performs this vmutex operation, no other reader process will be able to modify read count or will perform this if statement, execute this if statement, because they will be locked within by this pmutex operation, simply because we have initialized mutex, semaphore variable mutex to value 1. Okay. So, this ensures mutual exclusion of these two statements within this pmutex pair. In the essence, it ensures that this read count cannot be modified by more than one reader process at a time. And you have seen that if we allow more than one reader process to modify the value of read count followed by this if statement, what type of problem we will face. Okay, that we have discussed with respect to our producer consumer problem when we have tried to modify the value of count. Okay. So, to ensure that such type of problem does not occur, this access of this read count variable has been made mutually exclusive, and this mutual exclusion is guaranteed by this pmutex pair. Okay. Now, let us assume that initially there is no reader process or no writer process trying to access the file. Okay. So, first time one reader process is trying to access the file. So, the reader process will perform this pmutex operation, assuming that pmutex is successful because no other process is willing to read the content of the file. Pmutex is successful, so the process is given access to this read count variable and read count is incremented by 1. Our initial value of read count was 0. So, in this case, after incrementing value of read count by 1, the read count becomes equal to 1. So, this process now finds that read count is equal to 1, so it will perform this p-write semaphore operation. Okay. P-write will also be successful because initially we have said that there is no other process trying to access this file. So, p-write will also be successful. So, the reader process will perform vmutex operation and starts reading the content of the file. In the meantime, while this first process is reading the content of the file, if there is a second reader process who also wants to read the content of the file, so the second reader process will perform this pmutex operation. Okay. Because the first process has already executed vmutex, so pmutex for the second process will also be successful. It increments read count by 1, so now value of read count becomes equal to 2. Read count becomes equal to 2, so p-write will not be performed by the second process. Okay. It will simply perform vmutex operation and start reading the content of the file. So, I have two processes reading the content of the same file simultaneously, and we said that this won't create problem because none of these processes are going to modify the content of the file. Okay. Now, what happens if at this point any writer process wants to access the file? So, the code for the writer process is like this. The writer process will perform p-write operation. Here you find that the first reader process who has entered this critical region, it has performed a p-write operation. Okay. So, the writer process which also first performs p-write operation, it won't be able to execute p-write successfully because the corresponding v-write has not been executed yet. Okay. So, the writer process will be locked on this p-write operation, right. Now, here you find that since there are two reader processes trying to read the content of the file simultaneously, they will also come out one after another. So the first process to come out will perform p mutex, decrement the read count. It will check what is the value of the read count. If read count equal to 0, then only it will perform v write operation. Okay. Now we have two processes in this critical region. When one process is trying to come out, assuming that p mutex is successful, it will decrement the read count by 1. So now the value of read count will be equal to 1, which is not equal to 0. So the first process to come out of this critical region will not perform the v write operation. It will simply perform v mutex and come out. So even now, because v write operation has not been performed, the writer process will not wake up. So it cannot enter the critical region. It cannot write into the file. Only when the second reader process also wants to come out, that will also perform p mutex, decrement read count by 1. Earlier value of read count was equal to 1, so now it will be equal to 0. Now, because read count has become equal to 0, so the last process to come out will perform v write operation, and then finally v mutex and will come out. Once this v write operation is successful, then only the writer process will wake up from this queue, and it can perform this write operation into the file. Okay. So find that this mutex variable, semaphore variable, ensures mutual exclusion of this read count variable, whereas this semaphore variable write, it ensures that whenever there is any reader process performing read on the file, no writer process is given access to the file. Okay. However, more than one reader process can read the content of the file. Similarly, if there is any writer process is trying to write into the file, no other reader process or writer process will give an access to the file. Okay. So it is the first reader process to enter this critical region will perform p write operation, ensuring that even if there is at least one reader process, the writer process cannot get access. And it is the last reader process to come out of the critical region will perform p write operation. Okay. So the first reader process to enter the critical region will perform p write, and the last reader process to come out of the critical region will perform v write. Right. So find that such a complicated problem where we can allow more than one reader process to be into the critical region simultaneously, but whenever there is any writer process, no other reader process or writer process can be given access to the file. Even such a complicated problem can be solved using these semaphore variables, and that shows the power of semaphore variables and the semaphore operations that we have.
This may lead to the starvation of the write processes.
Yeah,
if we don't have a read semaphore, which is initialized to n, whatever the maximum number.
That is true. This does not solve the problem of starvation. It only solves the problem of mutual exclusion. Okay. Now, we have assumed that this p mutex operation and v mutex operation, they are atomic in nature. Then one question naturally comes that how to ensure that these operations will be atomic. Okay. So if you go into the Unix operating system, the Unix operating system gives the provision of semaphore variables, and it has also have the system calls to perform this p mutex, v mutex operations. Of course, the mnemonics is not really p or v. It has got some other mnemonics. Okay. Using those mnemonics, this p and v operations can be implemented. But again, that is a set of code, a set of instructions used to implement p operation and v operation. But then naturally the question comes, because it is not a single instruction, because it is a set of instructions, how do you ensure the atomicity of p operation and v operation? Okay. Now all the operations on the semaphore variables that are done are with the help of system calls, and this system call is a function. And the first thing that is done is, whenever the system call is executed, the first instruction within the function is to give the system highest priority for that process, because that will have highest priority no other operation can be performed until and unless the priority of the process comes down. Okay. So the first statement is to increase the priority to the highest level, and the last statement is to reduce the priority. Right. So though this P and V operations are to be performed by functions, but the atomicity is ensured by changing the priority level. Okay. Now, let us discuss about another kind of problem that we get in operating systems when we allow more than one processes to be executed simultaneously, even in time multiplexed fashion. A problem which is known as a deadlock problem. Now, what is this deadlock problem? We have seen that the major function of the operating system is to manage the resources of the system, the resources which are to be shared by more than one processes. Okay. And in such a case, we can lead to a problem like this. Suppose we have got two processes in the system. We call these processes P1 and process P2. Okay. And in the system, we have two resources, the resource A and resource B. A simple situation like this. We have only two processes, P1 and P2, and we have only two resources, A and B, in the system. Okay. P1, for its completion, requires both the resources A and B. Similarly, P2 also requires both the resources A and B. And their operations can be complete only when both the resources are available. Until and unless both are available, they cannot complete their operation. Okay. And the resources will be released only after completion of the process. Okay. Now we can have a situation like this. Suppose P1 has acquired resource A. So I have resource A, I have resource B, I have the process P1, I also have the process P2. So I have a situation like this, that P1, because it needs both the resources A and B, first suppose it requires resource A, and so it has put a request for resource A and it has acquired resource A. Because for its completion, it requires both the resources A and B, so I have a situation like this, that P1 has acquired resource A and in future it will require resource B. For P2, it has acquired the resource B and in future it will require the resource A. And we have also said that P1 will require both the resources for its completion, P2 will also require both the resources for its completion. And P1, once it has acquired resource A, it will not release resource A until and unless it gets B and its job is complete. Similarly, P2, though it has acquired resource B, it will not release B until and unless it gets A and its job is complete. Okay. So I have a situation like this, that P1 has acquired A and is waiting for the resource B to be free. Because until and unless P2 releases B, P1 cannot acquire it. Okay. Similarly, P2, it has acquired resource B and is waiting for resource A to be released. So you find that we have a funny situation, that P1 has acquired A, waiting for B, which can be released only by P2 after its completion. P2 has acquired B, waiting for A, which is to be released by P1 after its completion. Okay. P1 cannot complete until and unless it gets B. P2 also cannot complete until and unless it gets A. Okay. So you find that we have a situation that both these processes have acquired some resource, and it is waiting for the other resource to be released by the other process, which in turn is waiting for another resource which is acquired by the first process. And you find that in this situation, neither A will be released by P1, neither B will be released by P2, and they will wait forever in such a cycle, and they will never be complete. Okay, so this is a situation or a problem which is known as a deadlock problem, and this is a very common and a serious problem which is to be solved by the operating system, because in a system we have a number of processes working independently. They ask for different resources as and when they want it. Now the operating system has to find out that when to allocate which resource to which of the process, so that the deadlock will not occur in the system. Okay. Now there are various approaches to solve this deadlock problem, to ensure that deadlock does not occur in a system, because whenever there is a deadlock, it is an wastage. Okay. So to avoid this deadlock problem, the processes or utilization of the resources has to follow some protocol or some rule. The rule is, whenever a process wants to use a resource, firstly the process has to put a request for that resource. Okay. Now if that resource is free, then only the operating system will allocate the resource to the requesting process. Okay. And once the use of the resource is complete, then the resource has to be made free by the process who has requested for it. So we must follow a sequence that first the process has to request for the resource. After the resource is granted, it has to use the resource, and on completion it has to release the resource. Okay. Now in order to be able to give the resources to the different requesting processes, the system must know the status of different resources. Okay, that is, which resource is free or which resource is already allocated, if it is allocated, to which process it has been allocated. All these informations must be known to the operating system for proper management of the resources. Okay, so such information, status information of the resources is maintained in a system table. So whenever any request is made, the operating system refers to the system table to find out the status of that resource, and depending upon some criteria, it determines whether the resource can be immediately granted to the requesting process, or the requesting process will be asked to wait for some more time, after which the resource will be allocated. So it is never guaranteed that even if the resource is free, whenever I want, I put a request and I will get it. That is not guaranteed. Even if the resource is free, I may have to wait until and unless some more resources are made free, so that the operating system decides that even if my requests are made, in future it won't go into deadlock. Okay. So there are some algorithms which are to be followed to ensure that deadlock will not occur. Okay. Now, so this is the sequence in which the resources are to be requested, used, and released by the processes. Now let us say how to formally define a deadlock. I have just given the concept of deadlock and in which way the resources are to be used. Now a formal definition of deadlock can be given like this, that a set of processes is said to be in deadlock when every process in the set waits for an event which can only be uh, ensured by other process in the set. It is a set of processes, okay, I'll write it. So this is the deadlock definition. A set of processes is said to be in deadlock when every process in the set waits for an event that can only be caused by another process in the set. So in this case, what is the event? Let us come to this. P1 is waiting for an event. The event is B to be released. And this B can be released only by P2. P1 cannot release B. Similarly, P2 is waiting for an event. The event is A is to be released. And this A can only be released by P1. P2 cannot release it. Okay. So every process is waiting for an event which can only be caused by another process in the set, not by the same process. Okay. And that is a formal definition of deadlock. Now, as we said, that it is the responsibility of the operating system to see that the deadlock does not occur. Then the operating system must know what are the reasons which can lead to deadlock, or what are the conditions of deadlock. Okay. So if we know the conditions of deadlock, then if we can ensure that such conditions will never occur, then we can ensure that the deadlock will never occur. Okay. So you have to know that what are the conditions for the occurrence of a deadlock. There are 4 necessary conditions for the occurrence of deadlock. The conditions are: number 1 is mutual exclusion. That is, there is at least one resource in the system which cannot be shared by more than one process at a time. Okay. Say for example, a printer. A printer cannot be simultaneously shared by more than one process, because in that case the output of different processes will get mixed up, and from the printout you will not be able to understand which is what. Okay. So there must be at least one resource in the system which cannot be shared by more than one process. So that is mutual exclusion. That is the first condition for the occurrence of deadlock. Second condition for the occurrence of deadlock is hold and wait. Okay. That is, the process is holding some resource and waiting for other resources to be released. As in this case, P1 is holding A and waiting for B to be released. That is, hold A and wait for B. Similarly, P2 is holding B and waiting for A. Okay. So hold and wait is the second necessary condition for the occurrence of deadlock. Third condition is no preemption. That is, once a resource is allocated to a process, the resource cannot be preempted. Only the process will voluntarily release the resource. Okay. So that is the third condition. And the fourth condition for occurrence of deadlock is what is called the circular wait. Of course, we can say that this circular wait is an extension of this hold and wait, because it is the hold and wait which leads to circular wait condition. But even then, it is better to keep them as separate, because this will ease our analysis process of deadlock problem. And because these are the 4 necessary conditions for the occurrence of deadlock, if we can avoid any of these conditions, if we can ensure that at least one of them is not present, then we can ensure that the system is deadlock free. Okay. So we'll see more on this in the next class.